So there is a pointer. Excellent. Okay, so long waves climbing slopes of different roughness. Our work was carried out in Hannover at Large Wave Flume. It is rather, all collaborators from this team are from different trades. Myself, I'm a physicist. John T. Pearson from work as well is civil engineer dealing with sediments. Ira is modeling waves theoretically, and Artyom was her student at the time doing numerical simulations. So we're now digesting data, so I will really appreciate any comments, criticism, suggestions, whatever. So the flume. The flume is 250 meters from the wave maker to the beginning of the slope. It is our first experience of playing such a large toy, and really thanks to Stefan Schimmels who helped us with that. So we were surprising to be to have to cycle from the wave maker to the slope. So the slope is 1 to 6. We were keeping depth at 3.5 meters for all the experiments. We had 16 resistance wave gauges to measure the wave field. They were inhomogeneously distributed to be able to reconstruct waves as they non-linearly evolve from leaving the wave maker to approaching the slope. Runup was measured with the capacitance probe, which was 2 isolated wires which were stretched at a centimeter above the slope. There was some drawback of this technique, which I will tell later, but essentially we only can measure the maximum runup, and we cannot really measure the minimum runup, the minimum position of the shoreline. As roughness elements, we used 100 by 100 millimeters logs, literally across the whole slope. Waves were 20-second period, wave height up to half a meter at deep water. We were also using cameras. I will show you later sample pictures from these cameras. One for just generally monitoring and calibrating the run-up gauge, one for measuring the profile of the water near the slope. We also had ultrasound diagnostics installed, but we just tried to use it. Obviously, it was inferior to the one which was described 2 talks ago, so I don't even list it. Right, project. Initial aim of the project was to study effect of nonlinearity on the run-up height and to compare it with rather classic theories, shallow water equations, classic run-up theory, developed and test models developed by Ira. Initially we tried to test the influence of slope roughness, and we decided that our second series will be devoted to the slope roughness. So just I'll flash through a couple of slides with conclusions from the first series. First, we just demonstrated experimentally that steepening of the wave on the wave from the wave maker to the slope leads indeed to increase of the run-up height, and also testing different spectra of incident waves, narrow spectra and wide spectra. We have shown that statistics is such that occurrence of killer waves, of rogue waves at the shore is higher for narrow spectrum. Right, so I will flash through a couple of slides from the first part. There is a theory, analytical theory, showing that the run-up should increase as the result of wave steepening. So we compared results for nonlinear wave deformation with our experimental data, and it was more or less consistent. We also analyzed statistics of the waves which can be called rogue waves, rogue run-ups, if you like. And we found that indeed there is a difference between narrow band incident spectrum and wide band incident spectrum. This is some old slide just to show that it is indeed important because amount of rogue wave effects happening on the coast is relatively large compared, well, as a proportion of all such effects. Right, so second experimental series shown a few interesting results. What have we done? First, we tested the roughness. So initially the slope was covered with the plastic to make roughness nearly zero. And then there was logs put on it and different spacing between logs has been tested. On this picture you can barely see two wires which were capacitance probe, and you can also see this green thing which is the trace of the laser sheet which was used to measure the profile of the water. This is just view from the camera which was aimed to measure the surface profile. We do have these measurements, we don't know yet what to do with them. So any ideas are appreciated. And then we load it with as many diagnostics as we can possibly install, well, which could prove a good thing. We deal with roughness. Some motivation of doing this. So roughness affects the run-up in two ways. First, when you have run-up stage, obviously having roughness elements at the slope leads to the taking momentum from the incoming fluid. And as a result, if your envisaged solution is here, then the solution, well, then the actually observed wave run-up height will be lower. The other effect, which is, well, which looks more interesting to me, is that, well, and please comment what you think on it, is that obviously on the run down, due to viscous effects at smooth surface and due to this roughness, a tongue of fluid remains at the slope long after the wave run down. So if envisaged solution is here, there is a notable tongue of fluid remaining there, and interaction of this tongue, which runs down with the next incident wave, leads to the breaking of this incident wave, which basically spoils all theoretical predictions. So we done some experiments, which just to show set of diagnostics we had. It's like monitoring screen for all our diagnostics. Black ones are just data from the wave gauges. These three are near the slope which were used to reconstruction of the incident wave field. This reconstructed wave field, this green line, as you may observe, has nothing to do with sinusoidal wave. We can do nothing with it, but that's how the wave deforms when it reaches the slope. So if we use exactly the same wave but different slope roughness, then we can do some robust conclusions. So red is run-up gauge, 3 minutes. Come on, it was more. Right. Okay, so 3 minutes, 3 results. First, the most obvious thing to test is how much the roughness decreases the run-up. What we plotted here is black is the run-up without any roughness elements, and colors are the run-up with roughness elements. So we found out that there is a funny way of predicting how much is the influence of the roughness elements. So it turns out that the difference, for example, between blue and black in run-up height is exactly the summary height, sum of heights of the logs which were on the way of the wave. And it is more or less consistent for some range. Second result, we have measured force exerted by the wave on the logs, and we integrated those forces. Basically, we integrated these peaks, and what we found is that in this graph you can see the total momentum taken off from fluids when it goes up, total momentum taken off from fluids on the way down, and their sum. well, obviously those two thin lines are of different sign, but the main conclusion is that in total, roughness elements push fluid upwards. So roughness elements decrease the Runup height, but in total they push the fluid upwards. Which is an interesting result, I think, and this linear dependence is mystery to me. I mean, I cannot provide any hand-wavy arguments for that. Right, the very last thing, I don't have much time. Obviously, interesting thing is how the roughness of the slope affects the reflected wave. Well, what we did is we just plotted ratio of squares of the amplitude of incident and reflected wave, and plotted it for different wave amplitude, for different roughness, and we found that there is not much dependence. I mean, there is dependence on the slope roughness. There is effect on the level of several %, but not more than that. Well, do I have 1 more minute? Minute? Half a minute. Fine. The latest thing we tried to do is, well, obviously if you have long enough wave series, then visually it looks like if you have a wave, a big wave, which runs down, then this running down wave will inhibit the next wave. So what we try to do is, so these green are incident waves, so you have two waves of the same amplitude, but the wave before this one was lower than it, the wave before this one was higher than it. The thing is, which of them will give higher run-up on average? And the conclusion is, well, I'll not go into details. For different parameters, more or less consistently, you can see that if the previous wave was higher, then the next will give several % higher run-up. So the effect is opposite. So the previous wave increases the run-up by this wave. And one more conclusion is that when you introduce logs, this effect is less. So that's about it. I'll not list conclusions, I just told you.
Thank you very much, Peter. I know that you wanted to tell more. But I also want to give the audience the opportunity to ask questions. So please ask Peter a question. Mark?
Yes, I have a question. It's a very interesting topic you have been investigating. Thank you. With your analysis, are you able to identify which of the roughness elements contributes most in reducing the wave run-up? Is it those that are around the water level, the still water level, or those that are more up on the slope?
All we can tell is those below water level don't have effect.
No. Okay.
I mean, you appreciate that like one experimental run is like 2 hours when you increase amplitude from 0 to something. We have like 2 weeks in the latest. So I mean, we tried this and that. We measured forces only on 2 logs, one at the water level and one like 4 meters behind. I don't know which is more important. But I can speculate that probably higher ones, because the water layer is thinner, higher up the slope. But no definite answer.
Okay.
I think there's another question. Please state the question into the microphone, and everyone can hear. But the other people would also like to hear the answer.
I think the one which was just close to the shoreline was given the most. At least it was experiencing the most, the largest loading as well, because we were checking loading. But it was also one of the guidelines. Then since the heights were changing very much, so the number of loads affecting each waves were different. Yeah, because the run-up can reach just 2 second log, and yeah, you understand the thing. So because they are distributed along the slope, they are many, but waves have a change in wave height. Yeah, so for example, one reach only second one, another one reaches it experiences a number of them during the slope. But just comparing the difference, how it's changing for all difference in run-up height for all waves of all the different amplitudes. It was somehow, so I had the impression that it's the one which is at the shoreline, the basic ones, they give the, yeah.
Okay, that was the last question for this presentation. Thank you again, Peter.
I will talk about this one because it's the thing in which I'm more or less sure and on which I want to hear comments. So just to remind you, what was that whole stuff about? We have a slope, we have logs on it. We measure force acting on the logs. So we want basically to find how much momentum is being transferred by logs to the fluid. So if you look at the signal, then what we do is like this black is force acting on the log, well, pressure, force, whatever, acting on the log at the shoreline. This magenta is a log which is slightly above. We are more or less sure that these peaks are well resolved, so if you zoom it in, it is, we don't think we lose anything in here, and if you integrate them, you will get the total momentum which is supplied by fluid. So the thing is, again, this momentum, like total momentum subtracted from fluid on the way up. First funny thing, okay, so this is wave amplitude, this is total momentum. First funny thing, after certain wave amplitude, 0.1 meter is approximately log height, this momentum subtracted on the way up is constant. I mean, you increase the wave amplitude 4 times, total momentum is the same. I don't know why. And the momentum on the way down. The momentum on the way down is subtracted by logs from the water which slides down the slope. And well, obviously if you have a large wave, then you have a long time when this water slides down the slope. So it is like maybe not that strong force on logs, but is long time for which it happens. As a result, the total momentum subtracted from the fluid is growing. As a result, the total momentum given by logs to the fluid is upwards. So overall, logs push fluid upwards. However, yes. Please wait for a moment.
Suppose that there is a wave and then there is water lying above the log and simply resting there for a long time. Then that is the sign of momentum you're looking for.
It is not resting there, it is escaping under the log eventually.
Sure, but for some time it's simply resting there, so, and this is considered then as a momentum transferred downward on the log from the fluid, or it's a question?
Yes, but if you look at those signals, like arresting, you probably call this bit when it is negligible. Okay. But actually I would reckon like this, like big things when there is still flow over the log is contributing. So actually this log is at the shoreline. So there is not much time when water is resting in it. Yes, I understand the comment, but I don't believe this is the case. So it is due to the flow. So the funny conclusion is that although total momentum is up, the logs reduce the run-up height. Which means that logs somehow change the flow structure, making gravity to do more of work. Well, and if there are any comments on this, or any hand-wavy suggestions on why this is linear or why this is constant, that would be appreciated. Another thing could be that interaction of these tongue which runs down with the next wave causes a bore to form, and maybe this is the reason. So, well.
Do we have any comment for Peter? Suggestions? Maybe they will come during lunch. I'm almost sure of it. Thanks, Peter, for coming up in this way. I'd like to thank you all very much for